All right, so now we're going to take a look, maybe put the calculations on the back burner for a little bit. We're going to take a look qualitatively at the strengths of the conjugate acid or the conjugate base for a particular compound. And we'll start, first of all, with looking at the example of a strong acid. So we define strong acids and strong bases based on the ionization. So strong acids, and by the same extension, or by the same reasoning, strong bases ionize completely in water. That means this reaction goes 100% to the right. So if I have HCl, hydrochloric acid, a strong acid, okay, in solution, all I have are these ions. This is going to form these ions completely. So there's only ions in solution. And the reason for that is because the Cl minus, the chloride ion, when it's produced, doesn't have any affinity for the proton, so it doesn't recombine with the proton. It's not going to grab a proton from something else. It's not going to accept a proton from something else. So as a result, that conjugate base, which is the Cl minus, okay, so remember now, if this is my acid, right, when the acid loses a proton, it becomes a Cl minus. This is the conjugate base of that strong acid, okay? Because it doesn't have any affinity or doesn't want to pick up any H plus ion, it is then considered weak, right? Because it falls under that definition. So if you were to think, well, would the Cl minus react with water to accept an H plus to become HCl again? The answer is no, right? This is not going to happen. So really all you will be left with is the Cl minus. So what we find here is that the chloride ion on the Cl minus, right, is actually a weak conjugate base, and it came from a strong acid. That's the first thing. So a strong acid, we can use that to generalize, by the way. A strong acid produces a weak conjugate base. Now, if we have a weak acid by contrast, so something like HF, hydrofluoric acid, okay, so this is a weak acid because it's not one of the strong acids. So by default, that means it's weak. We'll notice here the arrows. It's an equilibrium reversible arrow, so that tells us right away that it's weak also. We're going to get small concentrations of these, okay, small amounts of these. And this equilibrium actually lies to the left, okay, because the Ka is going to be a fairly small value. So the equilibrium lies to the left. And what that means is when we produce this F minus here, this is the conjugate base now of the HF, because the HF has lost a proton to become F minus. This actually has a strong affinity for the H plus, because again, okay, being weak, this equilibrium lies to this side. So if this F minus is made, it actually grabs a hold of the H plus really quickly to form more of the HF, hence the equilibrium lying to the left side. So we actually do have this F minus grabbing a hold of an H plus from H2O to form back this original HF, the hydrofluoric acid molecule. Because it has a strong affinity, it wants to grab a hold, it wants to accept an H plus. That means then that this conjugate base here is going to be strong. So what we can say then, using this as a generalization, is if we have a weak acid, this produces or leads to the formation of a strong conjugate base. Now, the terms strong and conjugate base and weak conjugate base, these are strong and weak relative to the conjugate acids and bases. They're not strong and weak in terms of how we define strong acids versus weak acids, or strong bases versus weak bases, how we define those at the beginning of this section. So what we see then is that there's an inverse relationship And again, we're using these two examples as generalizations. There's an inverse relationship between an acid, we can say, or base, because the same trend applies, and its conjugate. So in other words, if I start off with a strong acid, I end up with a weak conjugate base. If I start off with a weak acid, I end up with a strong conjugate base. And similarly, if I start off with a strong base, I end up with a weak conjugate acid. If I start off with a weak base, I end up with a strong conjugate acid. Okay, and that's what this very useful table here in your textbook summarizes very well. So a strong acid leads to or has a weak conjugate base. So for example, nitric acid, very strong acid. The conjugate base here it's a nitrate ion. It's weak. It is not going to grab a hold of protons. A weak acid, by contrast, has a strong conjugate. So hydrocyanic acid, its conjugate is the cyanide ion that actually grabs a hold of H plus to form more of the HCN. And then the same thing applies to the bases. So strong bases, like the hydroxide ion, right? Its conjugate, we stick an H plus onto this, is water, and water, as you know, is a weak acid. And similarly now, a weak base, like the ammonia ion, the ammonia molecule, its conjugate will have an extra H plus, so that will be the ammonium ion. That is a strong conjugate base. A strong conjugate acid. Okay, so now that we have a general idea of how the strengths of the conjugates of acids or bases, how we can predict those, let's take a look now. We're going to bring back in some calculations. And we're going to consider a specific example. We're going to consider acetic acid, which is it's a weak acid, and we're going to also consider its conjugate base, which is the acetate ion. So we can write the expression for what happens with this acid in aqueous solution. So in H2O, okay, this reacts reversibly. This acts as an acid, donates an H plus to the H2O. We end up with acetate ion, and then we get our H3O plus. And then for the conjugate base, we'll do this in a different color, right? So acting as a base now, we can write the base expression for this in green over here. So we have our CH3COO minus, and we're going to see this reacting in H2O. So in H2O, to produce, so that's the acetate ion, will accept a proton. It becomes CH3COOH. H2O is going to lose a proton to become OH minus. I'm going to simplify the one above, the one in blue. So we're just going to show that this acting as an acid, it's going to lose this H plus. So that H plus is going to be off by itself. Like this, right? So we just took out the H2O on both sides of the first equation. So what we can do, right, we have our the equation for acetic acid acting as an acid. We have an equation for the acetate ion, its conjugate base acting as a base. We can add these two together, right? These are two equilibrium systems, so we can add them together. And as we've seen before, when we add equations, we can cancel things out. They're the same on both sides of the equation. So I can cancel out the acetate ion. I can cancel out the acetic acid. And what I end up with is H2O on the left side, reversibly to form H plus and OH minus. Right? And what I can also do with each of these, I can write out the Ka expression. So Ka here is CH3 COO minus times H plus divided by the acetic acid. And then I can also write the Kb expression for the one in green, the acetate ion. So my Kb there is, what do we have? CH3 COOH times OH minus divided by CH3COO minus, right? So this is nothing new. I'm just now writing out the expressions for the Ka and Kb within the same sort of conjugate acid-base system. So what we can see here now is if I write out, let me put in the state symbol so we can chart all of these things or track all of these things. This is, whoops, this is AQ. Okay, this is AQ. This is AQ. And then in the base version, this is AQ. Water is a liquid, as we know. This is AQ. And then hydroxide is AQ. So we end up with H2O liquid, H plus AQ, and OH minus AQ. So I can write this, the K expression for this resulting equation down here, right, which would look familiar to you. So K is equal to H plus times OH minus, right? And as you recall, this is actually KW. So when we looked at adding together equilibrium expressions before, we saw that when we add, so we're going to say recall this, when adding equilibrium equations, okay, what did we do to the K values? We multiplied the equilibrium constant values, right? So what if we're adding Ka plus Kb, or we're adding these two reactions together, we're now going to multiply them, right? So Ka times Kb. And what is that equal to? Well, Ka, right, I have my CH3 COO minus times H plus divided by CH3 COOH. And this times, we have CH3 COOH times OH minus divided by CH3COO minus. So I can do some simple math on this here. I can see that the CH3COO minus cancels out. One's on top, one's on the bottom. I can see the CH3COOH cancels. And what am I left with? Well, I'm left with H plus times OH minus. So, and what is H plus times OH minus equal to? Well, it's equal to KW. So what happens is, for a conjugate acid-base system, if you multiply the Ka by the Kb, you always end up with KW. Okay, we've just derived a very important relationship, and that gives a quantitative basis for that reciprocal relationship that we talked about before between the strength of an acid and that of its conjugate base, or between the strength of a base and that of its conjugate acid. So we know that Kw is a constant, right? We know, we talked about that already. Okay, so Kw is equal to Ka times Kb. So what would happen if the Ka value increased? Well, if Ka goes up, that means the Kb has to go down. And the opposite is true as well. If Kb goes up, the Ka has to go down. That's the reciprocal relationship that we mentioned before, where a strong acid is going to have a weak conjugate base, and a weak acid is going to have a strong conjugate base, right? That is based on this expression. And obviously, we can now, you take this and we can rearrange it to solve for Ka or Kb, okay, because this Kw, the ionization constant for water, that is a constant 1.0 times 10 to the negative 14 at 25 degrees Celsius always. Okay, so again, it boils down to a little bit of math. We're doing a little bit of algebra on here. The numbers are different because they're scientific notation numbers. They're really small values, but the idea is very, very simple. Okay, so let's take a look at applying that relationship. We'll take a look at the first one. So it says determine the Kb of the acetate ion. All right, and we're not given any other information. Okay, so we need here Kb of CH3COO minus. If we're asked for the Kb, right, B meaning base, this tells it that this is the conjugate base of something, of an acid, that is. So we can determine what that conjugate acid is. So what is the acid? Well, to find the conjugate acid, we just add an H plus onto this, and then obviously we're going to end up with the CH3COOH, right? That's your acetic acid. And that is something where we can look up the Ka value for for acetic acid. So Ka is equal to, for acetic acid, is 1.8 times 10 to the negative 5. Okay, and if we want the Kb, and we're given Ka, or we can look up Ka, we need the Kb, we're going to use the Kw relationship. Kw equals Ka times Kb. Notice that we can only use this relationship if we're looking at conjugate acid-base members, right? You can't have a whole different acid or a whole different base. It has to be the conjugate counterpart to the original acid or the original base. And again, we can tell that things are conjugates because they differ by a single proton. So if I need Kb, right, my Kb value would be equal to Kw divided by Ka. So I'm going to substitute Kw, we know is 1.0 times 10 to the negative 14. I just looked up my Ka, 1.8 times 10 to the negative 5. Stick that in your calculator, and you will end up with the Kb value of 5.6 times 10 to the negative 10. Okay, so it is that easy to find these Ka or Kb values, but you need to know, you need to approach the problem in a systematic way.